Today we will talk about Percona Server for MySQL InnoDB internals. So the talk is key performance algorithms. So we will discuss what we did, what changes we did to InnoDB to make it perform better. So this is going to be internals level talk. We will go into detail into several server areas, which are buffer pool, flashing, and the double write buffer. So, sorry. It's really helpful if you are familiar with those concepts already, but if there are any questions, feel free to interrupt me and to clarify something before moving forward. This talk is also going to be arranged somewhat chronologically, in that we'll start with 5.5, we'll move to 5.6, and then to 5.7, and on the way I'll try to show that how Percona engineering approaches those kinds of problems. I will try to show all the intermediate steps, what we did, what we found, what did not work, so how we arrived at the current solutions. Okay, let's start. So InnoDB has the buffer pool. Everybody knows that, right? And its premise is rather simple. I'm sorry. It's just a memory cache of disk data pages. Now, this cache is made of several different data structures. The first one, and probably the most used one, is the page hash, which is used for lookup, for actually finding the desired page in the buffer pool. The second important data structure, which is a part of the buffer pool, is the flash list. What it does, it manages the dirty data pages which have not been written to the disk yet. So the operations which happen to the flash list are adding the page to the flash list when you write to the page, and then on actual flash, removing the pages from it as they become clean. Being upon write to disk, there is no need to keep them on the flash list anymore. The next list is the least recently used list. Its purpose is when your data set exceeds the available memory size, to know which pages to sacrifice to make room for new pages. The sort of operations which gets done on this are page accesses, which move accessed pages to the front of the list to prevent them from being evicted. And before we discuss the other operation, we have to discuss free list as well. So free list is just some organized free space in buffer pool. These are empty pages which are there to be available for new page reads. So whenever we want to read a page, we take one of those pages from the free list, and we read into that empty page. So back to the LRU list. What we do when we have those two old pages, which fall off the end of LRU, we remove whatever content there is, and they put them to the free page to be used. So these are the main InnoDB buffer pool data structures: the page hash, the flash list, the LRU list, the free list. The next data structure which we have to consider is the double write buffer. The purpose of the double write buffer is to make sure that torn data page writes do not result in a data loss. If the server crashes in the middle of 16K page write, and the server itself, not a MySQL process, you don't want to end up in a situation where you have out of 16K page, 4K old image and 12K new image. You will not be able to restore from that. So what double write buffer does is that before writing to the data file, you collect a bunch of pages in the memory. Then once this buffer is full, you write them to the double write buffer first. Once this write is complete, then you write the data page again to its proper location in the data file. If a crash happens anywhere in this process, you always have at least one old or one new data page image, and you can restore. You're protected from the turn writes. Okay, now let's go to concurrency. All those different data structures, they are somehow protected for concurrent accesses by query threads and background threads. Page hash is used all the time. It's very important. It has its own page hash latch. Flush list has own mutex. And the remainder of the buffer pool are protected by a common buffer pool mutex. So it's an umbrella mutex which protects several data structures at once, which are only partially related. And it's going to be a problem, as we will see soon. And this also does not consider double write. We'll get to that in a moment. So it's obvious that the buffer pool mutex can get hot in such setup. It protects too many things. So this was recognized by Oracle at the time of 5.5 development, and they came up with the idea of sharding the buffer pool. And the shards were called instances. So now things improve a little bit, simply because you don't have one LAU to access to. You have 8 for LAUs. It's going to be less hot. But with this sharding scheme, there is still a problem. And the problem is that those instances are not equal at all. You can set buffer pool instance count to whatever large number you want. I think the maximum allowed is maybe 32. But even with setting for 32, you will find that you will still have hot instances. And those hot instances, they will have the same kind of problems with contention as the original single buffer pool mutex did. This was even recognized 6 years ago when that 5.5 development happened, but it was not addressed at the time. So what Percona did, so quite a long time ago, was to split all that, split the buffer pool mutex into proper finely grained mutexes, so that there is no single umbrella mutex. So we have LAU list mutex, we have free list mutex, and we have the rest. The rest is not being considered here, so that they're related to InnoDB page compression. We maintained that patch over several major releases, and for 5.7 we actually sent it to Oracle. We hoped they would merge it to 5.7. They didn't do that, but they merged it into 8. So now this thing which used to be Percona only now is given to the wider community. The buffer pool mutex split patch is now part of Oracle MySQL InnoDB. One last point is that those two solutions to reduce buffer pool contention are fully compatible. You can have both the mutex split and the instances. And this is actually what happens in the current Percona server because of the default. So that was 5.5, and life was easy there. Then this implementing the split helped a lot. So we are looking at the left side improvement. The right side is not today's topic. The actual numbers here do not matter. The versions do not matter. Just the shape of those two lines. This is a very typical graph for 5.5, where Oracle MySQL had lower performance and also regular dips. So that was nice, but then 5.6 came. We started working on 5.6 and we met problems. What we did was to port the buffer pool mutex split patch to 5.6 and then observe that there is absolutely no effect from that. And we could see that the mutex was hot before we ported, and after we ported, the new mutexes were not hot anymore. It's just that the throughput and latency neither did not improve. Naturally, we got very interested in the reasons of such a situation. And we found that it was InnoDB cleaner thread, which was introduced in 5.6, which was responsible for that. So what's that? What's that cleaner thread? What does it do? Well, in 5.5, the query threads, they performed flashing themselves if they needed to all the time. So a query thread is running and it sees that there is no free space in the buffer pool. A query thread will flash a little bit and will go on with this non-flashing business, but query business. 5.5 also had master thread, which did this flash list flashing for checkpoint age and dirty page percentage. But we are now focusing on the query thread flashing. So that was 5.5. Then 5.6, what 5.6 did was moved all the flashing from the query threads to the cleaner threads, to the master, to the new cleaner thread, and moved the flash list flashing from master thread there too. Okay, I'm sorry, that probably did not sound very, very cohesive. So now in this situation, we have increased thread specialization. And query threads are no longer responsible for making its own flashing and depend on the cleaner thread to do all the flashing. But is cleaner flashing good enough? Are cleaner flashing heuristics tuned well enough? And then we got 5.7. And it changed things even more. So now instead of one thread, we have many threads flashing. And how do they actually go about this coordination between themselves? So what is it's actually done here is that we have a single thread, one thread, coordinator thread, which is responsible for giving out work and waiting for the work to complete, and several worker threads. So time to flash comes. So the coordinator thread notifies worker threads that you will flash instance number 1, you will flash instance number 2, and I myself will flash instance number 0. Then all work is dispatched. What every thread does, it takes its assigned, doesn't work anymore, okay. Takes its assigned instance and first of all does the flashing from the LAU list for query threads to have pages, and then does the flashing for checkpoint age. And everybody do the same on the assigned instances. When they complete, they notify the coordinated thread, and the coordinated thread is responsible for sleeping until 1 second passes from the start of the previous flash, at which point it starts issuing requests again. Okay, so we try to use performance schema to see what's going on here. And we saw that in stock Oracle MySQL 5.7, we have a very hot buffer pool mutex in the second place, the orange line, and the blue line is something called doublewrite mutex. And it was very, very hot in this workload. And please note that this is a logarithmic scale, so it's actually this guy is really hot. But then we learned the hard way that if you take this chart and try to make a decision based on it, what to work on, you might be misled because performance schema data is incomplete. And since this is about flashing, the incomplete bits are very relevant, because out of all those multi-threaded flashing threads, only the coordinator thread is actually submitting data to performance schema. All the other worker threads are invisible. That's actually not good. So what we do then is we go to trusted poor man's profiler tool, and we get lots of stack traces to look at, and we see where time is actually spent. So in this scenario, what we see that the top aggregated weight of 660 weights, taking a mutex at this particular location, and this does correspond with the blue line in performance schema graph. This shows the hot mutex. What is not shown on the performance schema graph is the second top weight, which is as almost the same content as the mutex weight. So what's that? That's the doublewrite buffer, not only having a hot mutex, but also having something else. What is that something else? You look at the stack trace and you see above the doublewrite write single page. This single is a reference to something called single page flashing, which was put in here in Oracle 5.6, and we do not like this feature, so to speak. What is it? So whenever a query thread ends up in a situation where it needs a free page to continue, it checks if there is a free page available on the free list we discussed before. If there is one, no problem. Take a page, go on about its business. However, it is possible that the free list will be empty, that there are no free pages in the free list. What do? Well, then we do something called single page flash. We find one page in the buffer pool. We flash it, we double write it, and then we take that page as a free page. So this we did not like, because the actual algorithm introduces lots of latency, and it adds up to I/O and takes all the same hot mutexes. So what we did, we made the query threads lazy with that respect. Never ever flush by itself. If there is no free page, wait for it. A cleaner thread will give you a free page sometime in the future. Just sit there and wait until it does. So this we implemented already in 5.6, and it was very helpful here. And Oracle MySQL still does not do that in any version, including 8. Yes?
Is backup the default?
It is the default. Now, another aspect to consider, okay, so we are handling the situation of not having free pages better, but why we don't have them? How come we don't have them? We are supposed to have them in there's flashing ongoing, which produces them all the time. So why is that happening? So for this, let's go back to 5.7 multi-threaded flashing design. And if we review it again more critically, we'll find a number of drawbacks in this particular design. So first of all, let's assume the one-to-one correspondence between threads and buffer pool instances. And now for each thread, let's show the number of free pages at the time. So let's say the instance number 0 starts with a low count of free pages, and then it increases because of ongoing flushing here, increases, and then flushing stops, and query threads start taking them. So it is used up, and at some point they are all gone. So while we restart the flushing here, while we are here, the previous situation of not having single free pages will be relevant. That does not have to be a universal problem, of course. So this, let's say that instance 0 is actually the hot one. As you can see, instance 1 is not as hot one. It has enough free pages throughout the workload here. Okay, so why do we have this situation? That's because, first of all the threads serialize the flashing modes. It is only the LAU flashing which produces the free pages. Flashless flashing does not do that, but they are serialized in the same thread. Every thread first does the one and then the other. Why there is need for that serialization? There is no need for that. Another issue is that there is a synchronization between all the threads on 1 second mark. So let's say we are here. This thread is idle. It should start flashing right away because there are no free pages, but it will not do that. It will wait until 1 second comes, and only then it will start. Okay, so that's just a very natural design for a change in multi-threaded flashing. So what we did, we separated the flashing modes, LAU and flash list, completely. We removed any synchronization between the threads. We removed any synchronization on 1 second mark. And we implemented heuristics. When should the next round of flashing start based on the available free pages, the actual thing that the thread is supposed to produce. And well, I think this is a nice design, but I'm biased. So we implemented it, and we ran our experiments, benchmarks with doublewrite disabled to validate the design, to isolate the effect of itself, and it was very nice. Everything was flying. There was no single page flashes. There's no lack of free pages. Everything was working as intended. And then we turned on back the doublewrite buffer, and there was no improvement again. Okay, let's continue the work then. So in that situation, we again checked the performance schema, what's going on, and we found that buffer pool mutexes are not hot, because by that time we had the split patch. The removal of single page flash also helped with mutexes. So the top waiter here, this how do you call that color? Purple? I'm not sure. Line is actually undo lock related mutex. So one could think, okay, so if you enable double write back, you have to go and fix undo lock concurrency, which does not really make sense. So well, then we cross-referenced these results with PMP. And PMP already showed things that performance schema couldn't show to us. So then we saw that, so first of all, our log mutex is hot, which was not exactly seen in the graph before, but we also still waiting for something. What is this? What does this line of code mean? It's actually that wait loop when we removed the single page flashing. So this is that wait, when you, instead of flashing, wait for the page to appear. All right, so that's our code. Why it's not visible in performance schema? It's because we had a bug. We still have that bug in performance schema. This wait should be annotated. It's not. It's a recurring theme in InnoDB source code that performance schema does not have complete visibility into its internals, because some of the key annotations are missing, depending on what you need to look at. The next data we collected was to to see how are our flasher threads doing. When you do performance schema graph like that, this is a wall of your server. So what you have there is the aggregate of, let's say, 500 query threads and four flashing threads. Those 4 threads are not going to be exactly visible here. So we devised a way to get. Well, here we do not have to devise anything. This performance schema can support selecting threads. So we isolated cleaner threads and ran performance schema benchmarks again. So we found that we have, again, doublewrite mutex hot here. And then we actually started looking into doublewrite internals. What does that mutex do? So the doublewrite structure, data structure is shared. It's a single in-memory buffer. And everybody wants to add it basically at the same time. So that's what mutex does. It simply serializes access is there. OK, that's easy. But then we also checked PMP again, not only performance schema. So performance schema is helpful, but not completely. And what we see here again, we again see that there is some sort of weight here related to doublewrite, DBL-RW, not related to single page flashing that we removed. And it's, again, not visible in performance schema. Same bug. What does this weight protect? What are the threads waiting for? It turns out that they are waiting for the full doublewrite buffer to be flashed to disk. A full doublewrite buffer is 120 data pages. So you have to wait for that I/O to complete and fsync to complete. That's what you wait for. It turns out that it's a pretty long operation in terms of server time. And at this point, we understood that we must fix doublewrite. And one of the current buffer, it's one of the current properties is that it's a shared single buffer, and you have many flashing threads. Why does it have to be a single buffer? Any pages in the buffer, they have no relation to each other. There is no synchronization whatsoever between the individual pages in the doublewrite buffer. So maybe it does not have to be a single one. And we implemented multiple doublewrite buffers, each private to one flashing thread and not shared with anything. So it's private to one thread. It's not shared to anything. Means that all the mutexes go away. It means that all those threads work in parallel completely, both with the formally protected by the mutex operation of adding pages, and flashing itself is also parallel. So this is the proper design, I believe. We implemented this, and then we checked things again with the performance schema. And we see now that we have redo log mutex as the hottest one, which is fine. Which means that we sort of addressed what we need to with a buffer pool and doublewrite buffer. But by now we never trust performance schema data in isolation. So running PMP again, all the contentions are gone. There is one weight here, but this is not a weight which prevents another useful operation to complete. It's simply a wait. When you issue a I/O write request, you have to wait until that request completes, until you write out the data pages to their final locations. So it could be replaced with synchronous I/O, and it would just show write in progress instead of a wait. So with all this done, then we run throughput and latency benchmarks, and the difference with Oracle MySQL is pretty nice, I would say. So here we have the current server versions. So we have the latest Percona Server, which is as of now is 5.7.17. We have MySQL 5.7.18, and we have 8.01. And we have full durability settings, doublewrite enabled, flushed log at each commit. And we see that at a higher concurrency, the single page flashing and doublewrite buffer issues, they make the MySQL server go down. Whereas we keep performance flat when we reach peak one. So we are trying to be an independent performance expert. So we would stop. Otherwise, we would have stopped at this graph only. But we also had to try to tune the server and to find maybe there are workarounds with Oracle MySQL. So what we found is that limiting DB thread concurrency, it helped MySQL. Then if you limit in DB thread concurrency, then it goes, which is its peak performance point, then it kind of keeps flat for a while, even with all those issues. Another important issue which this work resolved was performance variance. Once a query has to do that single page flashing thing or wait for the doublewrite buffer to be emptied so that it can add a page there, all that waiting time, which directly involves I/O, is first of all unpredictable, and second of all, if it's significant because it's I/O involving. So that means that Oracle MySQL has lots of performance instabilities as well. So we can look at both throughput. That we can see that both throughput is varying, and latency is varying as well. Whereas with Percona Server, the picture is much smoother, especially for latency. There is still some variation in throughput. With InnoDB thread concurrency 64, we see that it helps with variation a bit, but does not eliminate it completely. So that means we can go to summarize what we did. So we explored I/O-bound workloads, writing I/O-bound workloads. And these can be characterized that they need 3 pages in a buffer pool all the time. Those 3 pages are needed in order to read something else in. And there are 2 ways to provide those 3 pages. One is the cleaner thread flashing, and another is single page flashing. So we concluded that single page flashing is bad. Or it doesn't matter if doublewrite is enabled or not. So we got rid of it. We implemented proper parallel LAU flasher design. Then we discovered that that doublewrite buffer bottlenecks they negate the parallel flashing improvements and need resolved too. So we made it parallel too, and it all worked in the end. Thank you. Yes?
Did you compare with doublewrite buffer just disabled?
We did that all the time because as we were developing prototypes, we wanted to isolate the effect of prototypes. And if we do flashing prototype, not doublewrite prototype, then we disabled it. We check the result with off, with on, and then only then we check the result with on. Yes.
What was the performance overhead of doublewrite buffer after all the?
At this point, I will not recall the exact number. On the first slide, I did not introduce myself. So my name is Laurynas, and it said Alexei also, the 2 authors. So Alexei could answer all those questions about the configuration. Unfortunately, he's not here. And any other questions? Okay, thank you.